All right, you're all right. What speed is that? 70 miles an hour. 70? Yeah.
70 miles an hour was at 5G. That's 5 times his body weight, pushing him down to the ground. Getting up to 80 will push me towards 7G. This is the big run then. This is the final run. Guy Martin going for a piece of history. Here we go. Listen to the revs rising. This is so exciting. Look at the vibrations on his body. The G-force is mounting. 72.79 miles an hour. How much further can he go? 78. It's getting up towards 6.5G. Can he go quicker than that? I think he's done 78 miles an hour. He comes down off the wall. The crowd love that one. He hasn't.
So here you've got an example of Guy Martin. He's an accomplished motorcyclist in terms of racing, and he's broken various world records. And in this instance, he's literally putting circular motion in a horizontal plane in action. And the comment was made about the number of G's that he was being subjected to. I think the thing you should appreciate is, if he'd gone faster, the problem would have been he'd have more G's, and there's only so much that the body can actually take. But that's a record-breaking effort there with a vertical wall. So just going through a couple of examples here, just the idea of, we're going to look at centripetal force in a couple of different ways, both in the horizontal motion, which is what you saw there with the motorcyclist, and here's another example here where you're going to see a sphere being rotated around this wooden circle, and the wooden circle is keeping the ball in its circular motion. If the circle is creating a force that causes it to accelerate. It's not changing in speed, but it's because it's changing its direction, we say that it's accelerating. But when you take that force that's being applied by the circle away, you can see it goes off in a tangential sort of direction. There's all sorts of examples that I could go through where we've got this relationship of a circular motion. If we think of the moon going around the Earth, okay, and why is that moon going round? Why doesn't it go off in any old direction? Well, it's the gravity of Earth that causes that. So we have a gravitational force that's pulling it in. It has a tangential velocity, but the force is pulling it in, creating that circular motion. If we look at other sort of actions, if we think about a circular motion in the horizontal, I know it looks vertical, but we're looking down from above, okay, and the idea is we've got an object that's moving around. It has a tangential velocity going out in the direction it's moving, but it's obviously turning, and that turning is created by a tension on the string that's the ball is attached to a string, and the tension is causing that force, that centripetal force, or centripetal force, in towards the center. We can actually look at it in just the straightforward horizontal. So if you imagine trying to create something which is moving that horizontal plane, maybe on a tabletop or in free air, or you might have a situation where you've got some sort of almost a conic sort of pendulum situation, but in a conic situation. And you can see not only do we have to deal with tension, and that's going to be at an angle, but we also have to deal with the mass of the object, gravity creating a weight, and we'll look at how we can sort of try and total up and get a net force acting on it. You can see actually if we break the tension down into two separate parts, okay, we've got the tension that's broken down into a vertical, which, if it's going to be a horizontal motion, it's going to be equal to the weight, and then the force acting towards the center, annotated here as T sine theta. Theta, by the way, is the angle at the top. It's the angle that the string creates with the vertical. So T sine theta is the centripetal force that's acting, that's causing the acceleration in the horizontal circular plane. Another example, maybe a better sort of demonstration of that cone. You can see there with the tangential, the red arrow showing the tangential velocity. That's the same idea, basically. Now we will move on to a vertical scenario, and you can see here now the weight is acting down at all points in time due to gravity. The tension on the string is going to change, and the guy with the bucket, the water bucket, was talking about that. You can see obviously the tangential velocity. But we introduced you to this idea of angular velocity. And there's relationships between v, the tangential velocity, omega, the angular velocity, the forces created by the tension of a string, the normal reaction due to that, that wooden circle created a normal reaction. If you take a bowl, if you go and take a breakfast bowl and a Malteser, next time you have some Maltesers, go to the kitchen, get a bowl, and actually just get that Malteser just to spin inside the bowl. Okay, it's just a gentle movement. You could have any sort of bowl sphere as well. If you have an object inside a sphere, and how that's gonna act inside that sphere or the bowl. It's easier to actually see what's going on in the bowl than the sphere. So in those instances, you've got centripetal forces occurring, and we will analyze it, break it down into component parts. So I've given you 3 videos now, and as a document that you can print off, PDF of summary of the formulas that we're going to use. And I would suggest you actually just read about centripetal accelerations on page 125 and 126. Then what we'll do is in the next sort of lesson I'm going to fire out at you, we'll actually start breaking down the motion in the horizontal circle and with some examples. Okay, thank you.